Alright, ready? Let's start by anyone is on here. Oh yes.
When is it valid to assume a free surface? And what's free surface?
Tau I equal to 0.
And what is it physically?
Stratified smooth. If we have kind of stratified smooth in the film zone of the slug, then that is valid. So slug flow, one part is film, right? If that film has a uniform surface, that's tau I equal to 0 for that case. No frictional pressure loss. And I will show you that when we do this kind of assumption, we arrive at something similar to double Hubbard. Good. Did you? Okay.
So you said we have to equal the numerator of the equation, the DHF. But that gives a critical height, right? What?
That's equilibrium height. Critical height is bottom part go to 0.
Yes,
Bottom part go to 0. That is a critical height.
But you don't use that critical height anywhere.
You use critical height when we do the full form of solving that equation. Okay, we will start at the height, whichever is lower, and then move on to the next point until the end. So we need critical height if we are going to use RKF45 or explicit Euler to solve that dz equation. Alright, let's start with this. Pressure drop equation. We start from Barnea, Taitel-Barnea full form, momentum equation. So I don't do anything, I just do the integration. Do the integration from the whole film length. 0 to LF, I should have parentheses, but you understand that. This integration sign covers this whole term. Integrate left side and right side from 0 to LF. Okay? Once we do that integration, so we have this one, the top equation, I just copy. Okay? This equation, so when z equal to 0, I can change from dv, dz equal to dvf, right? And vf is vtb minus v LTB. So when length is 0, VLTB is kind of VLRS. So when length is 0, we have VTB minus VLRS. When length equal to LF, VF will be VTB minus VLTBE. Or this, I can write it as VLTBI, initial point and end point. Okay, that's the first term. Second term is from that one, third term is from that one, last term is from that one. So basically we integrate from 0 to LF for Z. At that point, H go from HF as Z equal to 0 and HF as Z equal to DF. Just change the limit of integration. Yes. From this to this term become that term.
So these cancel out or just
this become this.
So what?
You can think about it as cancel out, but it's chain rule. Okay, but okay, it's cancel out. You can think about okay, this dz cancel with this dz and this dvf become that, but actually it's chain rule. Okay. And z equal to 0, vf is vtb minus that. So if you do the last question of the homework, you should be very well understand this. Okay? Same technique. Alright, left hand side, see I multiply HLTB on both sides. So left hand side multiply HLTB like that, and vf is VTB minus VLRS, right? So VF multiplied by HLTB equal to VTB minus VLS multiplied by HLS. So this term equal to this term according to X equation. Got it? You still remember X equation, Jason? What is the equation for X? Yeah, Wei-Sheng, what is the equation for X? VTB minus what? Okay, VTB minus VS, which is the same as VLLS, multiplied by HLLS, equal to VTB minus VLTB multiplied by HLTB, right? Okay, so based on that equation, we have this. And VTB and HLS, VLS, this term, it is constant. So we can move out from the integration sign. And inside the integration sign, we doesn't have anything left, right? So we move everything out from the integration. Then we have integration of dVF. Then we have VF. VF from the top limit, which is this, minus the bottom limit. Just do the integration. Okay? Do the math a little bit. VTB cancel. Then we get this for left hand side. Good? That's for left hand side. For, okay, that's left hand side. Then right hand side, I copy the equation. Just copy the equation. Didn't do anything. Did I? No, I didn't do anything. Just copy equation. The equation after we multiply by HLTB. Okay? And so I have HLTB divided by AF. That would be 1 over AP, right? Okay, just copy the equation. Make left hand side equal to right hand side. Didn't do anything, just copy it down like that. Okay? And so this term is this one, right? That is that one. And then we have green one. Green one come from this part, is it? This left hand side, that's a green one. So L, delta V, H, and another delta V. That's the green one. So I have green one equal, okay, sorry for this, but green one equal to brown minus that. Okay, and that brown term, this term is that term, this term is that term. Just copy it down, didn't do anything. Okay. Now we substitute into the global force balance and we neglect the pressure drop in the bubble. You still remember the global force balance that we had earlier? Global force balance, we have for Taitel-Barnea, we have this one, right? That's global force balance. And if we do global force balance, neglecting some term, we have that. Okay, that is global force balance. Put what we get back in here. Okay, do it at home too. Okay, put what we get in there. Then rho g sign that stay the same, right? What we put is okay. Actually, this one is the global force balance that I just copied here. Did I? Is it the same? The brown one. Okay, let's take a look at global force balance. I have this term, the second term, rho g sin theta HRTB, and I have rho g sin theta HRTB. So the brown term. This just copy, right? The first term is that one. Just copy, become that. Next term, tau s and LF. So tau s and LF. I just copy it down. So that is global force balance. This equation is global force balance. Just copy it. Okay. Just do the math, okay? Go back home and do it, please. Become like that, a little bit. So we have this. Alright? When we use, when we integrate free momentum equation from Barnea, we have left hand side equal to right hand side, right? And we can express the brown term in terms of green. So I change this brown by this green thing that I get earlier by integrating Taitel-Barnea equation. Just substitute it in. Okay? And you will notice something. Can you open the page that have pressure drop for double Hubbard? Which page number that have pressure drop equation for double Hubbard? Open page 90. Come on. Don't do just this, okay, Tolani. Be active a little bit more.
I don't have my textbook, so.
You don't have the book? Open page 90. Page 90. Is it page 90? Which page number that give you the equation for pressure drop double Hubbard? Page 90 has 3.79. Right, that's 3.79. You can see that this equation is close, but it's not exact. We have the first term in double Hubbard. We have the second term, this is acceleration or pressure loss. We can have the third term, okay, shear due to slug body. But we won't have the last term in double Hubbard. Okay. You don't have rho s g sin theta? Maybe I didn't tell you the right equation.
Yeah, it's not 3.79.
It's not 3.79? Which one? Yeah. So it's same as double Hubbard if you put double Hubbard in angle, okay? But it doesn't have the last term. The last term is equivalent to 3.174. 3.174. 147, not 74. 147. Page 104. Okay, page 104. Delta PU is rho g sin theta ls, tau term, and minus delta P mix. So this is equivalent to double Hubbard. And the green term is delta P mix. Okay, the green term is delta P mix. So it's like acceleration term. But if you look at double Hubbard momentum equation, okay, this is double Hubbard momentum equation. 3.174. Okay, 3.174 if we express delta P mix 47, 47. So we have this form, right? So that's double Hubbard. Double Hubbard doesn't have that term. Okay? But when we derive from momentum balance of Taitel-Barnea equation, we have that term. So this term that has to do with cosine theta, it is the change in the liquid height. Okay, it's the change in the liquid height. When we accelerate it, we not just only increase the velocity, but we lift it up, right? We also lift it up. So let's evaluate that term, the last term. Okay, delta P mix is when we derive from Taitel-Barnea, we have the first term, accelerational term, and the second term, which is lifting term. Okay, lifting term. And if we look at the lifting term, that cosine theta term, rho g cosine theta is not a function of z or hf, right? We can take it out. Good. And dHf, we can write it as dHf by dz multiplied by dz. Good. And we know that dHf, this term is 0. Right? Okay. Z is a backward coordinate. Okay, moving backward, that is z direction. You remember when you try to integrate, or you didn't try to integrate by using RK45? The governing equation, z is backward.
What
Okay,
did you say?
z.
What did you say? Integrating that.
You remember when you try to integrate?
Integrate?
When you try to get that, see the film profile, z direction is opposite to the flow direction.
But there is no integral. So
There's no integral. No, this one.
Integrating.
This one is no integration. So the direction of z is opposite to the flow direction. The direction of z. So my point is the slope of the height, this term is negative. Okay. The rest is positive. So the cosine theta term, the last one is
So it's not equal to 0. It's just like less than 0.
is negative. Okay. So my point is the last term is negative. Okay. The last term is negative. Delta P mix is always less than delta P A. Okay, because acceleration of pressure loss, this term is positive, right? VTB is greater than HRS, or VRS, and VRS is greater than VRTBE. Okay. This term is the same, and it is positive, but the last term that has cosine theta, that term is negative. Add them together, so delta P mix is always less than delta PA. So if we just assume, if we neglect the last term, it's not good. Okay. If we neglect the last term, we should neglect that term too. Okay. And this is what we are about to go through. Okay. Next, this part is from Taitel-Barnea paper. I just copy the picture and show you the final result, and we will derive it. Yes, Arya.
What about the pressure loss due to gravity in the field?
We should have that too. And the full form of that we haven't reached it yet.
Can you go back to previous?
The full form is 106 3.155. Can you open that? 3.155. That's the equation that we should use. Okay? And we are about to reach that. We are about to reach that. We are about to reach that. Double Hubbard doesn't have zero term. It neglects zero term. But we should. And now I will tell you why we should. Okay? So the top part, this equation from Taitel-Barnea paper, that is the solution that we try to reach. Okay? I just put it there first. And so if we use Taitel-Barnea momentum equation without considering dPdZ in the film zone, tau G, which is a gas frictional pressure loss in the film zone, and interfacial friction loss in the film zone, then we get that top equation. And that top equation is the same as the equation that we just derived, which is this one. Okay? This one, I said similar to 147 and 149 is not identical, but similar, same thing. Okay? We just derived this one, right? And you remember when we derive it, we neglect the tau I term, we neglect dPdZ term in the film zone. For the rule of thumb, okay? For the rule of thumb, when we have multiphase flow without any calculation, flow up, we lose pressure. Flow down, we don't gain any pressure. Flow up, we lose another pressure. And when flow down, we don't gain anything. That's the rule of thumb, okay? Rule of thumb means just approximation, don't do any calculation or anything. So when we have double flow stratified, we have pressure gain due to gravity, right? And have pressure loss due to friction. But most of the time, they kind of cancel and we don't gain, don't lose anything. But when we flow up, we lose pressure. Okay? So equation at the bottom, this one, that we already have it. And I will show that it's the same as what in Taitel-Barnea paper. When you look at what in Taitel-Barnea paper, the first term, it is a false balance, okay? The first term is pressure multiplied by area, and pressure at point B multiplied by area. And the second one is this kind of potential, okay, which has to do with the change in the liquid height. The second term is the potential that has to do with the liquid height. We are going to derive it. How do we get that term based on this? Now you can get the equation with these green terms, right? That's the top one.
The second term in the first bracket.
Yeah, we have it somewhere. Okay, let's move on. So we will go from this equation from the bottom to the top. Okay, the bottom one we just derive it by integrating Taitel-Barnea momentum equation, right? Remember that? So this equation, just to remember that it's derived from this part, and several terms is neglected. Okay, tau I is neglected, dPdZ in the film zone is neglected. So look at the last term. Integration from HF at z equal to 0 to HF at z equal to LF. So I just copy the last term that have cosine theta. Okay, the last term that has cosine theta, we can express it like first term minus second term. So first term has to do with 0 to HF at z equal to LF, which is upper limit. Second term is integration from 0 to the lower limit. Okay, the first term is upper limit, the second term is lower limit. And H inside HLTB, H is the this part, HLTB cosine theta, I move it out, and whole up, I have integration of the area. Okay, use dH to be dy. So this part is identical to what we have long time ago. You remember that? Akinolu? You still remember that lecture that we have?
You said it was a long time ago.
Not long time ago. Okay, which page? Which page that we have that we have B, that we do the integration? Still remember? What about 3.103? See 3.103?
Yeah.
Okay, 3.103, I can change from P bar HLTB to rho G something, right? You see that? So rho G whole up. Okay. Then from that we get this one. Okay. It is kind of similar. So rho GH give you kind of pressure. So from that we get these two equations. Okay. Directly from the one that we showed earlier. Okay. Once we have this, let's analyze the integration of HOA with respect to height. Okay. So when we do this integration, HOA can express as A film divided by A pipe, right? That's HOA. Okay. And A film can be calculated from B dy, correct? Film, area of the film can be the integration from 0 to HF B dy. Good. So B, which is the width, multiplied by height, but the width also change with the height. Okay. So AF is integration from B dy. So we have double integration. And if you look at it, when height at z equal to LF, final height, we call it HFE. Initial height, we call it HS, small h sub s, or height for the slug body. Or you can back calculate from HLTB, HRLS, right? Use HLTB equal to HRLS and get height. Okay. So the trick here is swap the integration limit. Okay. So first we do from dy dh. Okay, dy dh. So b is some function inside. We don't care, but we want to see at limit of integration. So when we integration from y equal to 0 to y equal to hf is not a constant. Small h sub f here is a variable. Okay, so I draw a picture between y and hf. So the vertical axis is y equal to 0, right? Y equal to 0, we get vertical axis. So we integrate from y equal to 0, this line, this our lower limit, right? Y equal to 0, to y equal to hf, which is this line. And this integration is bounded by hf equal to 0, which is this line, horizontal line. And hf equal to hfe, which is this line. So our domain of integration is just that triangle. Just that triangle, okay? But we integrate with respect to dy first. From y equal to 0 to y equal to hf. And it's bound by another limit. So it's a triangle area. This triangle area is the domain of integration. Doesn't have to do anything with the function inside, okay? Doesn't have to do with the function inside. So we swap the limit of integration. So we make sure that the area is still be that triangle. Okay, but this time we go from HF first. So we go from this line, which is the bottom one, right? So you see the vertical line here? Vertical line. So we calculate the function inside at that point and the function inside at that point. Okay, so we have we do the integration from hf equal to y, which is that line, to the top part. Top part is hf equal to hfe, which is that. So that is the integration limit. So if we integrate from the bottom boundary to the top boundary. So this limit has to be bounded by some domain of y, and it's bound by y equal to 0, which is this line, and y equal to hfe. Okay, good. So it's just double integration and just the trick of changing the integration limit. Very good. Have you studied this before in calculus? Probably. Okay. Siri? Yes, of course, right? No. Okay. Nanchandi, did you study this before? Is this in calculus or something? Changing the limit of integration for double integration? Calculus 1? Maybe 2 or 3. But you have all those, right? Yeah, you have seen it, believe me. It's just a math part, right? The purpose, what is the purpose of doing all this?
I'm asking you, it's not the math that's the problem, it's the so far, because
Everything is a problem. Okay. Everything is a problem. To fully understand this, you have to go back home, read it again. Okay? And it's not undergrad course that you understand everything right away. But okay, the idea is we swap the limit of integration. Okay? And I did it right. So we swap the limit of integration. On Wednesday, if you get tested to swap the limit of integration, can you do it? No. This is to make sure that you understand the mathematics which is related to the derivation. I cannot test whether you understand the derivation or not because it's too long, but I can test whether you understand the mathematics which is related to the integration or not. So if I ask you to how to swap the limit of integration, then you can do it for sure, right?
Math is not a problem.
Not a problem.
It's,
Yes.
it's the explanation.
It's the explanation. Let me explain you more. Once we do the math, we get this term. Okay. Once we do the math, we get this term. We swap the limit of integration. Okay. So we integrate the b is not a function of film height. So we can integrate it directly, and then we get HFE minus y. And for the green term, this integration, we do the math, we get this, right? Change the limit of integration. Once you do everything together, put it back in, this equation become this one, okay? 3.147. And the good thing with 3.147 is it is the same as the force balance from Taitel-Barnea paper. It is the same as that. Okay, it is the same thing. And when you look at it, you can see what is the missing term. The missing term is we don't have the last term, right? This full term. We don't have that when we do double half integration. So what we need to do is, okay, let me read this one and you go. If we use minus theta pu equal to rho g sin theta plus this equilibrium film thickness, neglect the film zone pressure drop completely, the acceleration term should not be included. This term should not be included. Okay? Otherwise, it will be wrong. This from Taitel-Barnea. And look at this term. So if we include the acceleration term, you get that line way off. Okay? If you don't include the acceleration term, you can get HF equal to HE, no acceleration, and then you get something close. Okay? So when you do the calculation, you may calculate this term, and you may neglect that. Okay, and don't include the acceleration term. Then it will be just fine. That's the purpose for you to know. See you Wednesday. Bye bye. More explanation for you.